Hi, in this video I'm going to be taking you through the Edexcel GCSE June 2016 computer science paper. If you haven't done this paper already, I'd recommend you do it because there aren't many Edexcel papers available for you to practice. Do all of them that you can is what I'd recommend, unless you're watching this like the night before maybe and you haven't got time, when obviously watching this video would be better than nothing. But try and do the paper in exam conditions. It's a pain to do, you just have to force yourself to do it. Sit down for 2 hours without your phone or the TV or your laptop, and just get it done because it makes a big difference. Then mark it, watch this video to see how I approach the questions, and use these. These are the grey boundaries here. So these are actually broken down for the exam and the control assessment for the 2016 cohort. So compare it against, obviously tally up your marks and compare them against these grey boundaries here, these ones, and see what you got. See if that's what you're aiming for. So it's 2 hours, like I said. So it's a long exam, but at least you have plenty of time to get those 90 marks. You can't use a calculator. That's quite important. But there's not a ton of maths, so it's not such a big deal, I don't think. So let's get started. Okay, so the first question on this exam is to state the purpose of network protocols for 1 mark only. So it doesn't have to be too detailed, obviously. So network protocols are essentially rules of communication. So they're needed in order for different devices made by different people in different countries to have this set way of communicating. So really, their purpose is to provide rules so that connected devices can communicate. So something along those lines would get you that 1 mark. We now have a diagram showing the internet as a network of networks, each square representing a computing device. State the name of the high-speed internet infrastructure shown at A. And this is not a tricky question, but it's asking about a very niche part of the specification. So if you know the specification in and out, if you've printed it out maybe, which is what I used to do, and just go through each point, then you might recognise this, or what it's trying to get at is this idea of the connecting backbone. I think that's what Edexcel call it. It's more commonly known as the internet backbone, which is really just kind of a high-speed infrastructure. I mean, infrastructure is what gives this away, really. It's not talking about like the actual media or the medium like copper or fibre optic. It's talking about the collective term for the infrastructure. And this is what is linking the ISPs and is what really bridging these network of networks. So it's a very niche part of the specification. If you get asked in the exam, which is unlikely for them to repeat it, just bear in mind this very, specific point. The second part is easier though, and I think everyone should really get this because topologies are not too hard, I don't think. You've got to state the name of a network topology shown at B, and this is a ring topology. So that's all you need to write for this. This is a star topology. It's got this central node, and this is a bus topology. You also need to know about the mesh topology, which I might struggle to draw here, but let me try and do it as like a star, so like this, like a pentagon. Each node is connected to each other node, so something like this. Is that right? So this, if I've done this right, this would be a full mesh. And a partial mesh would be if like it was missing some of these links. So you can also have partial meshes. So it's not always a perfect kind of link. It's not always a perfect link. It can still be a mesh topology if it's sort of partial, because obviously the larger it gets, the more physical wires you need to connect the devices. So bear that in mind. Okay, we've got a really easy 4 marker here. We have to identify the type of network used in each situation out of the 4 different types of networks: local area network, wide area network, personal area network, and virtual private network. So the first one, a delivery driver using a hands-free kit to connect to his mobile phone. This is the personal area network because it's in his local vicinity, just on his person, really. We then have a dental nurse using a computer to look at digital x-rays stored on a server in the basement of a building. So this is just confined to one building. So this would be a local area network. A manager able to access as if he was in a different place. So that's kind of give away bits of virtual private network. That's kind of a point of VPN. It acts as if you're somewhere else when you're not. And then we have finally, an office in Tokyo sends emails to its customers, whether in New York, Paris or Delhi. So this is all over the world. This is a wide area network, so probably the internet. So data transmitted over a network is sometimes encrypted. State one reason why data encryption is used on a network, just for 1 mark, so you can keep it quite simple. So really encryption is there to keep your data, your information secret, private, secure, whatever you want to call it. And it does this because it scrambles it up so no one without the key can understand it. So let's say to keep, just wanted to info secure, because unauthorized people cannot understand it. Logically following on from the last question, we're looking at the Caesar cipher algorithm, which is used to encrypt and decrypt text. It's a very simple algorithm to do this. So the whole point of encryption is you go from plain text, which is readable, to ciphertext, which is unreadable, and then you, the people who know how to encrypt it can then decrypt it. So we've got a digit as our plain text, and we apply a shift of 3 to get our ciphertext. So Caesar cipher basically just replaces the letter in the alphabet with 1, however many along. So it's easier to show you than to explain it perhaps. So I'm going to write out the alphabet just to try and demonstrate this. Okay, so with digit, we're going from D first of all, and applying a shift of +3. So we're going from D to E to F to G. So now we're replacing this with G. So our first one in our ciphertext is G. Then with I, we're going 1, 2, 3 to L. With G, 1, 2, 3 to J. We have I again, so we can save time. And then T, we're going 1, 2, 3 to W. So this isn't readable, obviously, but in terms of this being secure, it's very easy to crack this, which is why it's unlikely that banks are going to be using Caesar cipher to encrypt people's data. So we now have to do the reverse process. So applying a shift of -2. So if this was the encryption stage, we're basically going backwards this time. So if we're encrypting it, we go D to B if we're doing digit again with -2. But because we're doing the reverse process, we have to +2 to this basically. So we're going from Z +2, it just wraps around. So we're going to A to B. So that's what we're doing. So the confusing bit here is the fact that you're dealing with like a double negative in a way, because you're doing reverse of a negative. But hopefully that makes sense. Then G, we got to go forward again. So H, I, L, M, N, Y is A. Probably guess what word this is. Where are we? P, and then it's going to be Y. So it's going to be binary. So I think if you get this answer, you know you're pretty much set in a computer science exam. It seems unlikely this will just be a coincidence. We now have a couple of questions on binary. They're usually not worth many marks, to be honest. I think people sometimes assume binary is going to be a massive part of the exam, but really it's meant to be quite simple, to be perfectly honest. First of all, we're doing binary addition. So you just have to remember some simple rules. It's the same as normal addition. Oh, that's awful. So like 0 plus 0 is 0, 0 plus 1 would be 1. But you have to bear in mind when you have 2 1s, because we're only dealing in base 2, we write down a 0 and we carry a 1, and then 1 plus 0 is 1, 0 plus 0 is 0, 1. Then you have this again, so 0, carry a 1, 0, carry a 1, and that's it, really simple. It can get more complicated if you end up with like 3 1s, because you've carried 1 from before, and you have to add this up. And what you do here, you write down a 1 and you carry a 1. So that's just how it works. It kind of collapses into this being like 0, carry a 1, and then 0 plus 1 is 1. So that's where it comes from. But that's the difficulty you're going to get. And occasionally you'll go over, but that's sort of a different question. That's called an overflow. So now we have to convert this byte into hexadecimal. So hexadecimal is base 16. binary is base 2, and they have this interesting, well, I say interesting, this relationship, which is why we use hexadecimal as shorthand. With 4 binary, with 4 bits, you how do I explain this? So 2 to the power 4 is 16, and 16 to the power 1 is 16. So this comes, this is going to come in later actually, because I've seen my question, it's about to come up. This is saying how many combinations we can represent with 4 bits, because we're dealing in base 2, this is our base of 2, this is our base of 16, because it's base 16, and this is how many combinations of 4 bits we can represent, so that's 16, 0 to 15, and then we have the same with 16. So basically, with 4 bits, you can represent with one hexadecimal digit, you can represent 4 bits. So that means we can split up this into 2 lots of 4 and just deal with them separately. You could convert this big number to decimal and then convert it to hexadecimal, but it's easier to deal with the smaller numbers. So let's do this bit first. So 0, 1, 1, 0, you kind of have to convert to decimal as like an intermediate step. So this is 2 plus 4, so this equals 6 in base 10. This is base 2. We often do a little suffix or prefix just to show what they are, what base they are. And so this equals 6 in base 16, because hexadecimal shares the first 10, it shares 0 to 9 with decimal, and then it has 10 as A, 11 as B, 12 as C, 13 as D, 14 as E, 15 as F. You don't go up to 16 because you've obviously got 0, so that's 16 in total. So 6 is the same. If we then look at the other side, the other nibble, 1, 1, 1, 0, this is going to be 8 plus 4 plus 2, which is 14 in base 10, which is equivalent to E in hexadecimal. So basically, this is a lot of faff just for 1 mark, and obviously I'm going into too much detail, but basically the answer is 6E. We're now doing the reverse process, going from hexadecimal to binary. So again, we just isolate the digits to make our life easier. So let's deal with C first. C in base 16 is, looking over here, is 12 in base 10. We can do equivalent here. Is equivalent to, so 8 goes into 12 once, remainder 4. So that's what it is in base 2. God, and you can see this relationship between 1 hexadecimal digit to being 4 binary digits. This is what I was trying to get out here, even if I didn't explain it very well. So now we have to look at 4, and 4 in base 16 is the same as 4 in base 10, which is 0, 1, 0, 0 in binary. If you're confused with any of this, I've got a video that covers this, and there are loads of videos of binary and hexadecimal on YouTube. It's really important you know this, because these are so easy marks. You should really be getting these. So just to write it in full, we can't just leave it as 2 parts. The answer is 1, 1, 0, 0, 0, 1, 0, 0 in base 2. Okay, we now have to show that 256 different numbers can be represented in 8 bits, and this is only worth 1 mark. And this is going back to what I was trying to explain earlier. I don't know how well I explained it really, to do with 1 hexadecimal digit equaling 4 bits, and to do with combinations. So what the format for this is, as the base, you write the base of the numbering system. So we're looking at binary, so you write 2, and then the power, the exponent, is how many we're looking at. So we're looking at 8 bits, so it's 2 to the power 8, which equals 256. And basically what this is saying is you can represent 256 unique characters with 8 bits. So if we're looking at this in terms of whole integers, this means you can represent 0 to 255 in a byte, but this isn't really relevant to a question. This is the bit it's looking for, just this part of it. So to give you another example, like your PIN number or your passcode for your iPhone, maybe just a 4-digit number. You're dealing with decimal, you're dealing with 0 to 9, so your base of 10, and then you have 4 in if it's a PIN number or a passcode, and this equals 10,000. So you have 10,000 unique PIN numbers or passcodes or whatever. So you have your base, your numbering system base, so it's 16 if it's hexadecimal, 10 if it's decimal, or 2 if it's binary, and then you raise it to however many you've got, and then that's your answer. So this is what this is trying to say. we have to then state one characteristic of a lossy compression algorithm. This contrasts with lossless. And compression algorithms just obviously reduce the size of a file. And lossy algorithms work by actually selectively deleting part of it. So part of the data is not needed as much as the other bits. So yeah, the most obvious characteristic is data is, let's say, permanently lost. Whereas a lossless algorithm just sort of rearranges it and stores a bit more efficiently. So they're not as effective as lossy algorithms, but obviously you don't lose data, your signal doesn't get degraded as much. We then have to identify an example of lossy compression. So the answer is JPEG out of all of these. To be honest, it's more that I know that JPEG is lossy rather than not knowing that the others. I don't really know what TIFF is, or I mean it's obviously lossless, it's not lossy. But it's more that I knew that JPEG is. I think there's a list and a specification of ones you need to know, so maybe to have a look at, just have a look at the wiki pages of that. I don't know if I cover it in my video, but yeah, that's the answer. So the next question is on Cartesian coordinates, and these are just normal coordinates. Cartesian is maybe a word you haven't come across before, but it's just normal coordinates, that's what it means. So we've got a turtle which used to draw on a Cartesian coordinate system, and it begins with the origin. So you can see the turtle is like facing up at the start, and it follows this program, and you've got to write the final location using these coordinates. So it's going forward 3 firstly, so it's going up to here, and it's still facing upwards. So it turns right 90 degrees. This is what this means. So it goes facing this direction, but it hasn't moved. It goes forward 5, so 1, 2, 3, 4, 5 to here. So it's still facing this direction. It turns left 180 degrees, so it goes to face this direction. Could go right 180 degrees, obviously. And then it goes forward 3, so 1, 2, 3, so it ends up here. So final coordinates of this is 2, 3. So obviously you write the x coordinate first, so you do it in brackets. So you can get a mark for each of these, so it's really easy, each x and y coordinate. So yeah. Question 2 begins with a bit of information about Charles, who's a programmer. It doesn't really matter, but we have to identify the legislation that applies in each situation for 3 marks. So again, these are usually pretty easy, these questions. So we have the EU Cookie Law, the Computer Misuse Act, and the Copyright Designs and Patents Act. Even without knowing much about them, you have to know a little bit. It's covered in the last video I made in the series. It's a bit of a pain to learn about, a bit of a pain to teach really, because it's not very interesting. But you could probably guess what they are from their names. So, teenager given a copy of a computer game for her birthday, she gives a copy of the game to her friend. So this is going to be to do with the Copyright Act. You can't just give away games or anything covered by this act to people. University student tries to gain access to government computers. This is going against the Computer Misuse Act, because this is all about sort of hacking and yeah, watch a video. I forget what it's about without having to look it up. And then storing small files on the user's computers to track the use of its website. That's what a cookie is, but it's not telling them. Well, now thanks to this derivative, you have to have that little pop-up at the bottom of each website telling you that they're using cookies. So that's the answer for this question. So another similar question, we have to identify the type of programming language most suitable for each situation. So we're distinguishing between high-level programming languages like Python, Java, C#, and low-level languages like assembly code. So the first situation is keeping a list of computers that needs fixing. Not a very complicated programming task, so you might as well use a high-level programming language. They have list data structures or arrays or whatever, but low-level languages are a pain to do anything like this. I know from experience, so you'd want to use a high-level language. Another bit is, the next situation is increasing the speed of part of a computer program so it runs in 1 hour instead of 20 hours. Well, you're not going to get a massive speed difference in high-level programming languages by altering stuff, but you can at the low level when you're dealing with things like the CPU clock speed. So this is much more applicable for low-level languages. Keeping track of how many users log into the company's file servers each day. This is again a relatively simple programming task if you do it in a high-level language. A low-level language doesn't really have structures designed for things like this necessarily. When writing a program for a new computer processor needs to be done really with a low-level language, because you're dealing directly with the hardware. There's little translation that gets done. So again, that should be really easy, 4 marks. Apologies for formatting here, but we've got some pseudocode given to us and we have a few 1-mark questions to do with it. So we first of all have to state the coding technique that trials could use to make the pseudocode easier to understand. So the 3 things on the specification are indents, comments and descriptive variable names. Well, it has got descriptive variable names, it has got indents, so the third option is comments. So yeah, the comments are the most obvious one usually, and this is the one that's missing out of those 3 that Edexcel want you to know about. We then have to state the name of the subprogram shown in the pseudocode. So subprogram is just like what it says really, a self-contained unit within a program, and we've got a function here. A function is a subprogram, but it does ask us to state the name, not the actual type. So if you wrote down function, you'd get it wrong because the name is cubenum. Other subprograms are like methods or procedures, so it's not just functions. State a range of line numbers which show a selection statement. Well, selection statements are to do with branching, and that's what if and else statements do. So it's this bit here, this block of code, not this extra line that's kind of added on. That's just like a print statement, the equivalent of. So 18 to 22. We then have to state the line number on which a variable anum is a local variable. Well, anum is first assigned up here, where it's a global variable, and then it's used in this branching statement, but it's still using anum as the global variable. But you can see here that it's getting passed into this function as a parameter. So this is where it's getting used as a local variable first. So so 25 is correct, but it's also being used in line 27. So you could also write line 27. Because this is anum here is now not this anum, it's now using whatever's being passed in. So that's where it's a local variable, and then we've got to state where it's a global variable. So I mentioned that's right at the top because any part of this program can use this now because it's declared of global scope. So it's line 10. Part C of this question is asking about binary again, and we have to complete this table to show the place value of the ones to the right of a decimal, so to the right of this binary point, and it's a binary real number, so we're dealing with fractions here. And one of the 2 ways we can do this is with fixed point notation, the other is floating point notation, and fixed point notation works in a very similar way to normal binary works. So I notice here that the columns double each time, the place value columns, and this is because this is 2 to the power 0, 2 to the power 1, 2 to the power 2, and so on in this direction. And it's the same the other way, so it follows a pattern. So this is 2 to the power minus 1, this is 2 to the power minus 2. So 2 to the power minus 1, as you should know from maths, is a half, and this is a quarter because this means 1 over 2 squared, which is a quarter. So this is the first part of this question. We're going to have to convert this binary real number to denary. And to do this with binary, you just multiply the column headings by the row. So 0 times 4 is 0, 2 times 1 is 2, plus 0, plus a half, plus a quarter. So this is, well, 2 3/4, or 2.75. We've then got to state the number of bits in a nibble. Should be the easiest question of the paper. This is just the answer is 4. You have 4 bits in a nibble and 2 nibbles in a byte, which is 8 bits. So the answer is 4. For the third part of this question, we have to write an arithmetic expression to show the time needed to transmit a 10 kilobyte file at 10 megabits per second for 2 marks. Not an easy question this, because it gets a bit confusing with the units. So it's not asking us to actually work out the time, it's asked us to show how you'd calculate it. Obviously this is a non-calculated paper, so it'd be a bit unfair. So, first of all, speed is, let's write this out here, speed is represented by bits per second, so this is bits per second. That's sort of what you need to appreciate here. And really we're looking for the time needed, so we have to rearrange this to get it in terms of the quantity of time. So in a normal way to rearrange an equation, this would end up being the time unit, so let's just write second equals bits over speed, because we're multiplying both sides by second and then dividing by speed. So this is what this is our format we're going to write it in. So we effectively have how should we talk about this? Let's break down 10 kilobytes into what this means. So kilo, the prefix kilo, and this is where it starts to get a bit complicated, because obviously in physics, kilo means 1,000. You know, you've got a kilometre. But in computer science, unfortunately, we're dealing with base 2 with binaries, so we deal with 1024, and we want to get it in bits because we want to be consistent here. So I'd always recommend you reduce it to the base unit, so in terms of seconds and bits, which are kind of the base unit we're dealing with. So we then have 8 bits in a byte, as we talked about a bit earlier. So this is where it's broken into. So to get this number into bits, we're looking for, first of all, we've got 10 kilobytes. We've got to multiply it by 1024 because that's the prefix kilo, and then by 8 because we want to get this into bytes. Into bits. We could just do a lowercase b there. Now for 10 megabits per second, this is going to be, so mega is the next one up, so you have kilo, mega, giga. But when we're dealing with speed, for whatever reason, this is now in terms of 1,000, so it's how it's used in normal physics, or, well, when you're dealing with base 10. So I don't know why this is, it's a pain, it's confusing, but it's just one of those things in computer science which is a bit iffy. So we're dealing with 10,000 now, so we have, let's do this properly. So we have, first of all, we have 10 of them, times 1,000, which is mega, times 1,000, which is kilo, because that's the prefix before, and then that's it, in fact. So this is just converting it to the base units. So now we have to sort of plug it into our formula. So let's just get rid of this. Now using this equation, we're going to write the bits on the top. So this was, we just worked out, was 10 times 1024 times 8 over 10 times 1,000 times 1,000. So I think you could leave it like this, or you could tidy it up, but you want to make your life easier in a non-calculator exam. There are other answers to this. I'll put them up on screen now that are shown on the mark scheme, but this is how I'd personally approach it. Again, it's a pain with the different, well, it's not really standardized, but when you're dealing with file sizes, it's 1024 usually, not always, but when you're dealing with speeds, it tends to be in terms of 1,000. So yeah, that's just how it is, unfortunately. So I'll put the other answers up on screen now. The first part of question 3 is actually another tricky question, potentially. I don't know how well I covered this in the video, I can't actually remember, but it's hard to tell what Edexcel want sometimes. So I've had to look at the mark scheme for this, just to make sure I answer it, exactly right. So we're talking about file management, which is one of the functions that the operating system performs. You have to know quite a few of these. Always a pain to teach. And so we have to describe how an operating system organises files. I mean, you might, even if you hadn't learned this, you might be able to answer this just from your knowledge of computers. And it's a 3 marker, so we're looking for 3 distinct points. That's usually how it goes. Like here, a 2 marker, you get a mark for each, for the denominator and for the numerator. So describe how an operating system organises files. Well, they're stored in this hierarchy, where you have your root folder here, like your C directory, and then you have all these sort of child files. So this is a tree structure, and that's an awful diagram, but that's what we're looking at. So we have, our first point here should be that files are stored in a hierarchy. That's our first mark. And then we need to say that the name for these subfolders or subfiles are, so that's our first mark. We then need to say that these are called nodes, or all of them are called nodes actually, the subfolders or the files. So let's say a node, and this is the key term we're looking for, which is why maybe you would lose a mark here if you didn't know that, is a, let's say, folder / subfolder, because if it's for root, it's not really a subfolder, or just a file in this structure. And then the third mark would be just to continue this by saying, and I don't know, the root folder is the top node, or you could say the parent node. So they're looking for very specific bits here. They're looking for this kind of this hierarchy, they're looking for that word, they're looking for a node, they're looking for root. So it's always a pain when exam boards, you know, get this specific, but that's just the reality of exams, unfortunately. The next few questions are on websites and networking as a whole. So the pages that Shanila designs will be accessed via a web server. Describe how someone will access the pages using the client-server model for 2 marks. So it should be relatively straightforward, this. So the way this works is if a client, your web browser, makes a request to the web server for this desired web page, which is then sent back to the client. So let me write this up. The whole point of the client is to make requests to the server, and the server is there to serve the client by returning stuff to it. So that's just how it works in this model. We now have to do a bit of HTML. So we have to write the HTML code. It gives us the kind of base tags you'd always have, so you don't need to worry about those. We have to write the HTML code, need to format the text socket and open-ended, so this bit here, this list, oops, that's not good, as shown above, for 3 marks. So if you know HTML, this is a great 3 marks, but if you don't know HTML, you might be panicking at this point, so it's important you learn it, and CSS when you're revising. This is something I didn't really cover in the videos because it's like learning a programming language in a sense, a simpler one, so you just need to go and look up videos on YouTube or look in your textbook and it should teach you from scratch. So this is a we need to define an unordered list here, just because we're dealing with bullet points. So an ordered list would be numbers, so this is an unordered list. So this uses the let's do an indent here, the UL tag, unordered list, and we've got to do a closing tag as well. So we've always got closure tags, and then we need to actually define the list objects, so socket and open-ended, so li, and then just write socket, and then close this, and have I got enough space to do open-ended, and then close this, and that's it. So just to recap, this is both of them are unordered lists, because we haven't got, if it was an ordered list, it'd be like 1, 2 instead of a bullet point, and we then just need to define the actual elements, or the actual bits in the list, the actual bullet points here. So this would get you those 3 marks. Alright, so Shanila is planning to use libraries in the code for the website. State 2 reasons for using libraries in code. So these are this external code source that you use really to save time, but that's a bit unspecific for the exam. So the most obvious reason in my mind, and in my experience when coding, often the most long-winded part of the whole sort of project is testing, and library code should at least have been tested before. So let's say it has already been tested or debugged, or whatever you want to say. Also, library code is usually code that is going to be used a lot, or let's just say it can be reused many times. So it's often quite generic, and you can use it many times, so it saves you time overall. Both save you time, but they're not specific enough to get you an individual mark, I wouldn't have thought. So moving on to Shanila's program here. Days of the week are numbered, 1 for Monday up to 7 for Sunday. So she's writing a code to determine whether it represents a weekday or weekend day. I'm going to complete the following pseudocode to show the logical operation. So this is and, or, and not. These are the 3 basic ones. So if day is greater or equal to 1, something, day is less than or equal to 5. So this is going to be for a weekday, it's got to be both. It's got to be both. So this is and. If a day is equal to 6 or equal to 7, it's going to be a weekend. And then here we have a bracket. So let's look at the bracket first. This is what gets evaluated first. So if a day is greater or equal to 1 or less than or equal to 7, so this is going to be and again, because this is basically our range. So it's going to send an error. So if it's not in this range is when you'd want to send an error. So you kind of work this out through power of deduction a little bit, but you really need to learn what each of these do. So and is for most exclusive. You have to have both sides of this to return true, or you can have either side true to return true, and not just does the opposite of what your input is. So you just have to learn these. Part D is either going to be a question that you turn to and are delighted about, or are terrified of if you haven't revised properly, because it's on SQL and it's sort of hard to wing SQL, although it is like pseudocode, so it's maybe not such a big deal if you haven't revised, but not that I'm advocating that. So we have a table from a database, and we have to write a SQL statement that reports the ID and description fields, so these two fields. Fields is another word for column. For all records, records another word for row, where the ID begins with the letter G, so we're going to have to use a wildcard operator here. We're going to have to then sort it in ascending order. So the wildcard operator we're going to be using is the % here, and we then you can use the keyword ASC for ascending order. The opposite would be DESC for descending order. So we first of all need to select these two fields from this table, and I might be able to fit this on one row, but it's not a big deal. So select ID and description. Yeah, I'm going to have to do it on 2 rows, it's not really a big deal. From the table name, so table product. Apologies for the handwriting, it's getting even worse. And then we need to actually specify this condition by using a where statement. So for all records where the ID begins with the letter G. So we then want to do, the simplest way to do this is with obviously where ID, and then let's use like, where ID like. So we need to do. So let me explain what this % does. So this is a substitute for either 0 or more characters. So we use it to essentially. Okay, so let me just write this out how I'd do it. So you do G, because we're starting off with G. Then you put the % sign. So what you're saying here is, you're saying you want to start with G, and then you can have anything else here. So we're just looking for G at the start. So we don't care what's after it particularly. It could be nothing. It could be something. In this case it's just numbers, but we're just substituting. This doesn't literally mean we're looking for % sign, it's looking for any other character after G. So if we were looking for G, or no, let's say if we were looking for just 1 in it, you would do a % sign 1 % sign, and it would just look for 1 in the middle of one of these strings, or look for 1 at all. So that's what we want, and then we have to order it by ascending order. So you just do order by, in capitals, ID ASC, and that's it. That's our 4 marks. So I've done it on 4 different lines, but you could compact it a little bit. For question 4, we're told that Manuel was interested in understanding the relationship between hardware and software. Describe what is meant by the term stored program concept for 2 marks. So this is the idea that both data and instructions are stored together in main memory. So then the CPU can actually fetch them from main memory, because obviously distinct hardware devices, and then decode them and execute them like you learn about in that cycle. So it's the idea that they're both stored in memory. We then have to describe what's meant by the term virtual machine for another 2 marks. This is quite a difficult term to describe in such a short answer, but really a virtual machine is a way of allowing you to simulate or emulate another computer on a computer. So you're kind of, usually it's there to use another operating system on your current operating system. So for example, using Linux on Windows. So it's a way of simulating another machine, which is why it's called a virtual machine. So to put this into words, let's say a VM allows one computer to simulate another computer, like I say, usually allowing a different operating system to be on that computer, to reside on the machine. So we have a 4 marker. We have to explain the difference between the sequential and parallel computational models. So sequential, they're just executed one after the other, sort of in the normal way. But in parallel, the kind of process is kind of split up into tasks, which are handled by 2 different maybe cores or processors or machines. Then you kind of have to recombine it to get your solution. So in sequential, it's one after the other. Whereas in parallel, tasks will be split up, or some instructions will be executed by different processors. So they need multiple cores. This is just multiple processors on the same chip essentially, and then you have to, so for results are then recombined. Because you have like multiple workers working on the same task, it's usually faster. But it's not, directly faster. So, if you have 4 cores operating at a clock speed of 2 gigahertz, that doesn't mean you've got 8 gigahertz in total if you have 4 cores, because it's obviously not going to be totally efficient, and not all programs are going to be optimized for this. So bear that in mind. It's not it's not a direct relationship. We have some pseudocode for an algorithm that calculates the area of a circle with radius of 5 units and uses this procedure subprogram. And he wants to change it so that the area of any circle can be calculated using this method. And we have to write the change pseudocode in the box below. I haven't got a box, so I'll just do it here. So what it's asking, at the moment, all it's doing is just calculating it just for 5 units, because it's got 5 here. But you want to adapt it to calculate any area. So basically you have to use a parameter. So you can pass in your parameter. So so let's just adapt this. So we need to basically put something in brackets and then use this variable name here. So we start off with just our calling statement here. So what we're going to call our variable, let's just call our variable radius. So I've just copied this line, replacing our parameter, or sorry, adding our parameter to it. It doesn't matter what you call this word, it makes sense to call it radius because that's what it is. And then we just have to copy this again, but replace 5 with radius. So that's it, that's all we've changed, just this bit here, adding the parameter basically. A parameter is just like a local variable used to pass in data to a subroutine, or subprogram, sorry. And it just allows you to kind of generalize a subprogram, because it's very specific at the moment. It's just dealing with 5, which isn't that helpful. If you want to change it, so this is a much better way to do it. So we have a 5 marker here where we have to implement a binary search algorithm. If you've learned your algorithms, there's a lot of them you need to know, to be honest, for this course, then this will be golden. If you haven't, you might be struggling. So the way binary search works is it continually divides by 2, discarding the bit of the list that it can't be. So it needs to be ordered. This is ordered, so that's all good. So it's probably easiest to show you this actually. So the first thing we do, we need to divide it by 2. So we get our middle point, which is our pivot. So the middle is here. And what we do, this is our number we're looking for, 1683. We need to compare this to 2248. So actually, first of all, this is the first one we're visiting, so we write down this here. And then our sublist is going to be the lower part, because we compare our target number to the one we visited. And if this is bigger than this number, we can discard this bit, because we know this isn't going to include our number, because we know it's ordered in ascending order, and the fact that this target number is larger than our our visitor number is larger than our target number, we know that this isn't going to be hidden there because it's ordered. So this is our sublist now, 837 1529, and there we are. And then we are now just dealing with this, and the middle of this list is 1529, and again our sublist just becomes our target number, actually, because we can discard this because we can look at our target number and compare it to our visitor number, and it's bigger, so anything smaller isn't gonna have it. So our sublist now just becomes our target, but we still have to kind of like follow it through and just search it. So we write down it, but then we found it, so we finish, hence the box is grayed out. So it should be a really easy 5 marks if you've learnt it, but make sure you learn all the algorithms. They're not actually that hard, but you just have to force yourself to really learn how they work, and hopefully my video shows you enough examples so that you understand it. So Manuel's been pretty busy. He's now working on logic for an exclusive OR operator, and this can be implemented using our 3 basic ones. So you don't need to know about exclusive OR for this course, but there are lots of other operators that are implemented using the 3 basic ones you do need to know about. So we have to complete this truth table to show Q for 3 marks. So let's take it step by step. So first of all, we need to do A or B. So for OR you need just one. So this is going to be the only one that's not, the first row is the only one that's not 1, because we haven't got a 1 in either A or B. The rest of them have at least 1. Then the next column, so we have to do 2 bits here. So let's do the bracket first. It's always how you should do it. A and B. So you need, that's not good. Jumping ahead. So A and B is 0, but we're doing the opposite of that. So we write down 1. A and B is again 0. So for and, you need both to be 1. So in fact, all of these are going to be 1 except the last one, which is 0, because we're doing the opposite of the bit of the brackets. So hopefully you can follow that. And then we're now using Q to do R and S. You've got to be careful that you're following the variables used here. So R and S, 0, 1, 1, 0. And this is what a exclusive OR looks like. Question 5a is the kind of inevitable 6 marker. You're going to get at least 1 in your actual exam. It's a quality of written communication question, so you have to show, good spelling, grammar, and punctuation. So you can't just do it in bullet points. You won't get the 6 marks if you do 6 points in bullet points. So as you can see here, I've been lazy and just copied the mark scheme. I think I'll lose the will to live if I try and write this up on my graphics tablet. And actually, I say this quite often actually, but the mark scheme can often be quite a good source of notes. I mean, usually the mark scheme doesn't explain to you at all how you answer a question, which is kind of understandable because it's not really for you, it's for the examiner. But in some cases, like here, it is quite good notes. Although, they're not going to repeat artificial intelligence in your exam because there are other emerging trends you can look at. So make sure you look at the list. I cover them in my last video in the series. But it's good practice, and I would recommend you sort of adapt this question for the other ones. So I think one's DNA computing. I think quantum computer came up a couple of years ago. I forget what the others are. So just adapt it to the other ones, because you may get this question, which is quite a nice question. Some of the characteristics, the ways in which it may be used, and the ethical issues. So just to quickly talk about this bit here, you have to have relevant points from the 3 categories. You can't just ignore, say, the ethical issues to get the full 5 or 6 marks. So some of the ideas I come up with characteristics, I would, like I say, if I were you, I would just do a little spider diagram as part of your revision for the other topics, which I've forgotten about. So AI is just this branch of computer science based on sort of mimicking human aspects of intelligence, and it combines quite a lot of fields, which we talked about in my video, I do remember now. Some of the uses, the simple ones like game playing, but also things like working in factories and natural language and processing. This is quite a big one. And ethical issues are probably most obvious with artificial intelligence, life-death decisions, and quite an important one is the economic kind of effect of AI. in that they're going to be replacing often low-paid human jobs, and so there's going to be unemployment caused by that. You need to kind of train people so that they're not going to be unemployed all their life because AI is taking their jobs. Do they have a right? I guess that's an ethical issue that seems a bit abstract at this point, but maybe in the future it will become more concrete. So yeah, that's it. Like I say, I wouldn't revise AI. I wouldn't say not to revise it, but they're not going to repeat AI 2 years in a row. You would highly doubt. So use a question like this. This is quite a nice template for a question to prepare for what they could ask you on one of the other topics. Okay, so you now have a couple of assembly language questions to finish off the paper, and this is over 2 pages by the way. I've had to combine it. It looks very daunting, and hopefully I'll be able to prove that it's not as hard as it maybe looks on first appearance. Assembly code always looks daunting because of how simple it is. So this is the actual program down here. They always give you some extra information about what each of the instructions mean. You don't have to remember them necessarily, although you should really be familiar with them. It saves you a lot of time. And we have to complete a trace table showing the changes in the values of these 3 registers during the execution of this assembly language program for 5 marks. So you need to step through this and jot down what is being stored where, what values are being stored at each point. So let me just try and just talk you through this. Hopefully it's big enough for you to see if you're watching like your phone or something. So first of all, we have a step where we're initializing our variables for the first time, just here, and that's really what move does. It's like a variable assignment. So the hashtag here equals immediate addressing, so we're actually moving the literal value of 1 into this register, or 2 or 4. So register 3 starts off with 1, register 2 starts off with 2, and register 3 starts with 1, register 4 starts with 2, and register 5 starts off with 4. So that's our first line in the trace table. And then we move into this, the next bit. This is a label, and so is this, L1 and L10. So they're used to branch to. So we have to compare 0, the literal value of 0, to the contents of R5 here. So R5 currently has 4, and we're comparing it to 0, so it's not equal. This is branch if it's equal, but it's not, so we just ignore this line for now. I realise you can't see my cursor, so I'm making movements of my cursor when you can't see, so that's a pain. So we're ignoring this line at the moment, the line 249. Then we have to multiply, and if we go up here to see what actually multiply does, so it multiplies Rm with Rs and stores it in Rd. So it's storing what R3 times R4 is, which is 2 in R3. So we write down 2 here. This is our next kind of logical step. And then we move on to the next line, which is sub. So subtract 1 from R5 and put it in R5. So R5, 4, so 4 minus 1 is 3, so we write it down. And then we branch back to L1. So we do this and do the process again. So we compare 0 to R5. It's not equal, so we just ignore the branch if equal line. Multiply R3 and R4. It's 2 times 2 is 4. You store it in R3. And then we subtract 1 from R5. So we write down a 2 here, and we branch back to the compare line. So it gets very repetitive. So once you get the hang of it, it should be pretty straightforward. So again, compare 0 to R5. It's not equal. 2 is not equal to 0, so we ignore the branch of equal line. And multiply R3 and R4. 4 times 2 is 8. We put down 8 in R3. Subtract 1 from R5 is 1. And then do the same process again. 8 times 2 is 16. And we write down a 0 here. And we then, so we are back. So if we've just put 0 in this stage, we then branch back to L1, compare 0 to R5. It is R5, so we branch of equal, we go to the end of the program, which is here. So hopefully that makes sense. I can't tell how much that made sense. Hopefully it did. I stand by what I said about it looks complicated at first, but actually it's relatively simple. But this would get us our 5 marks. So you do a line for each stage in the program. You're going to have gaps. That's normal. Some people assume you just fill it up but you don't. You leave gaps if only one register is being changed at one step, and there's plenty of extra space here which is not needed. Okay, we have the last three parts of the paper on this slide. Fortunately, we're nearly there. So we have to now state the purpose of the algorithm we just looked at, and I've crudely copied the trace table from before to demonstrate what it does. I can't tell if this is an easy question or not, to be honest. I don't know if most people would get this, to be honest. So the purpose of this is to calculate, in this specific example, 2 to the power 4, because 16 is our answer. We stop when we get to 16, which is what 2 to the power 4 is, which is also the same as, so you can see 2 is in R4 to start off with, and 4 is in R5. So it's really calculating R4 to the power of R5. So whatever's in R4 at the start is calculated to the power of R5, whatever's in there at the start. So that's what it does. You kind of just have to get that just by looking at it, really. I don't know if the majority of people would have got that or not. It's only 1 mark, so it's not a huge deal. But that's the answer. We're then told that the assembly language instructions, like those above, are made up of 2 distinct parts, and using just this instruction as an example, state the name of each part of the instruction. So this is move is the opcode, and this bit here is the operand. So operand means data, really. This is the data that's being used in this calculation. This is the actual operation called opcode. This is just the terms we use when we're dealing with assembly code. But I'll get us our 2 marks. The last 3 marks of the paper are for actually implementing this low-level program in high-level. So I'm going to do it in pseudocode. Just so you can use any programming language or notation that you know. So don't do a flowchart. I'm sure you wouldn't. Yeah, just do either pseudocode or whatever language you've learned in school. I'm going to do pseudocode because that's the generic one, and that's the one you'll see in Edexcel's mark scheme. So first thing we need to do is actually initialize our variables here. So in pseudocode, the convention that Edexcel used doesn't actually matter if you do it exactly like this. We'll keep the variable names the same. So to 1 set R4 to 2, and set R5 to 4. So this is the first stage. We then need to do this loop, essentially. And what we're doing, to implement this condition, I'm going to do a repeat loop. So because we're repeating until R5 equals 0, you can see here. So let me just write this here. I'm going to run out of space inevitably. Repeat until R5 equals 0. This isn't really a loop construct you see in high-level languages exactly like this, but pseudocode you can kind of do what you want, to some extent. So what we're doing, we're setting R3 to R3 times R4. We use an asterisk to do multiplication, and then we're setting R5 to R5 minus 1 in this bit here. And that's it, actually. This is the body of the loop here. And yeah, you can see how much simpler a high-level language equivalent is compared to the assembly code. That's just the reality of high-level languages. But that's it. That's our 3 marks, and that is the paper complete. So hopefully it was useful. Yeah, good luck in your exam.